Welcome back to Numerical Methods. Today we're going to begin covering our last major topic for this course, which is partial differential equations. Just as a reminder, last time we finished up boundary value problems, which are going to lead us into our partial differential equations. We sort of had two different methods for solving these boundary value problems, the shooting method and the finite difference method. The finite difference method is what we're really going to concentrate on as we move into partial differential equations. We also talked about Dirichlet and Neumann boundary conditions. Remember that Dirichlet was, we would set a value at one point, and a Neumann boundary condition was where we would set a derivative at some known point. Today, what we're going to start covering are partial differential equations. We're going to go and evaluate finite difference methods for two-dimensional systems. In addition to our Dirichlet and Neumann boundary conditions, we're going to introduce Robin's boundary conditions. After we've done that, we'll go through an example of implementing partial differential equations, and then we'll talk about time-dependent explicit implementation of partial differential equations. And then next time we'll go a little bit deeper into some more other topics. But let's start out our discussion today by talking about what a partial differential equation is. A partial differential equation has this general form: partial squared u partial y squared plus 2b times some function, and we'll come back to what this function is in a second, times the second partial derivative of some dependent variable u with respect to x and y, plus c times some function of a second partial derivative of u with respect to x, plus d times some function. Notice that we have this second derivative with y, the second partial derivative with x and y, and then this second derivative with respect to x. And then this d sitting out here is got no second derivative dependencies. These functions can be set up as a series of, can be classified further into being a linear, quasi-linear, or nonlinear equation. In the linear terms, in a linear equation, each of these pieces here, here, and here are only a function of the independent variables. So I don't see u popping up. I don't see any partial derivatives popping up. I only have, some function maybe of x or y or some constant. I guess that's sort of out there in that B. Quasi-linear is where we have these function values that may contain the independent variables x and y, like the linear, but then they may also contain the dependent variable u and or first derivatives of that dependent variable. Nonlinear is going to extend further out, where we're going to have these values, so x, y, u, but then also these second derivative terms that may also come into play. So here we may have a second derivative times a second derivative. Right. So these are going to be our general forms of differential equations. Additionally, we can further classify these differential equations based on how much weight can be put on each of these terms. So here I can sort of expand out these terms. If I group all the second order problems, second derivatives with respect to x, with respect to both x and y, just y, and then the first derivatives, we can form different forms of the equations. So an elliptical term would be where this b squared term, so the cross sort of second derivative minus the terms of a and c are less than 0. In other words, this cross second derivative is going to be less in magnitude than the weights given to the single dependent variable second derivative. If they exactly match, this is called a parabolic piece. If if that cross term is bigger, this is called a hyperbolic second order PDE. And then if g is 0, so there's no constant out here, this is called homogeneous. The solutions of some of these problems, especially in terms of analytical solutions, are going to be based on which of those forms are. And we're going to focus right now on these elliptical forms. Okay, so now that we've sort of got an idea of what these PDEs can look like, let's talk about our different types of boundary conditions. So we have Dirichlet and Neumann boundary conditions, which hopefully you're feeling pretty comfortable right now. This is the Dirichlet, or our first kind boundary condition, says the values of our dependent variables are given at fixed values of my independent variables. I know what a value is at a certain point. Neumann says the derivative of dependent variable is given as a constant of the independent variable. So it's like fixed. I know that the first derivative of the dependent variable with respect to the independent variable is a constant or is a function of the independent variable. So this would say this could be a constant or could be something that depends on x, so f of x. The third kind is called Robbins. Here, we have, it's sort of like the Neumann boundary condition where we have a derivative, but in this case, instead of we actually have the dependent variable over here. So the derivative of the dependent variable is a function of that dependent variable. Right? So this is going to come up in more complex partial differential equations. For today, we're going to focus on these two, and then we'll get to Robbins next time. Okay, so let's go through a few examples of different types of PDEs that we encounter a lot as engineers. So the first type of equation is called the Poisson equation. This would say that the partial derivative of u, the second partial derivative of u with respect to x, plus the second partial derivative of u with respect to y, is some function of x and y. In this case, we need boundary conditions. We need to know what's happening on the different edges of our equation. We can also have a subset, a specific case of the Poisson equation called the Laplace equation, which we see a lot in things like fluid mechanics, that says that partial derivative, second partial derivative sets is equal to 0. Once again, we're going to need boundary conditions. Oftentimes, particularly in, say, heat transfer, thermodynamics, reaction engineering, we see the heat equation. In this case, we have not only a dependency on some spatial term, so here, but we also have some time dependence. So here we have partial u partial t is equal to a partial squared u partial x squared plus f of x and time. Right? So we would need a boundary condition to deal with this second partial derivative of u with respect to x, and some initial condition to deal with this time piece. So while we've we can make this even more complicated, right? We could add in, partial squared u partial y squared, and then we would need another set of boundary conditions. Regardless of how we end up having these formulas set up, we're going to sort of take the same set of approaches that we did for our initial value and boundary condition problems, particularly within the finite difference approximation. Let's first talk about the boundary condition partial differential equations, and then we'll come back and talk about places where we need both boundary and initial condition problems. Why we're going to start with the boundary condition problems is this is going to be quite analogous to our one-dimensional boundary value problems that we covered in the previous unit. The idea is we're going to break our problem up into different nodes. This time, instead of having the nodes only be in one dimension, we're going to have them in 2 dimensions. Same idea, we're not going to cover it, but you could then go into 3 dimensions, 4 dimensions, whatever, as the problem becomes more complex. We're then going to convert our ODEs into a set of finite difference problems on each node, and then we're going to solve them either using linear algebra or some sort of nonlinear solving technique like Gauss-Seidel. So let's look at an example linear elliptical problem. Let's solve this following ODE. Here we have the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y is some function of x and y. And to make this sort of physical, let's say that this is going to equal to 0. So the first thing that we need to do is break our problem up into nodes. I've drawn over here an x-axis and a y-axis. And then what we're going to do, just like we did before, we're going to put a whole bunch of nodes along the x-axis, and then we're going to repeat them up along the y-axis. So we end up having all of these nodes. These are going to then represent, go from 0 all the way out to some n plus 1 number of nodes up here, and then some n plus 1 number of nodes up here. You can sort of pick whichever one you'd like, depending on the confines of your problem. Then we can label each node in our system just like we do for our matrices, where that first index I is going to represent the x direction, and that second index j is going to represent our y direction. We can go left to this point I minus 1j, or right to this point at I plus 1 comma j, or we can move up and down in the y direction by going to I comma j plus 1 or I comma j minus 1. These 4 points are going to be what is most interesting and pertinent. Okay, so now that we've broken up our problem into nodes, we're ready to convert our PDE into a set of finite difference problems. All right, so we're going to break this up. So let's go in and see how we can break this up. So we're going to tackle each of these one at a time. So let's say partial t squared partial x squared. And now we can start remembering what our central difference formula is for calculating a second derivative. Remember, if I have a partial derivative, with respect to x, I change my x direction. So I maybe look right. So I go I plus 1 comma j without changing the y direction, minus 2 times I comma j, plus look now to my left at the same y point. So that's I minus 1 comma j, all over delta x squared. Right? So this this is just substituting my definition for a partial derivative using a finite difference. Remember, all the way back to when we were talking about calculating partial derivatives from numbers. Now we're just going backwards. Okay, I can do the same thing for partial squared t partial y squared. So now I'm going to change t only in the y direction. So I'm going to look, if I'm at this point, I'm going to go up, I'm going to look up here. So that's still at point I, but now it's at j plus 1. I'm going to subtract off 2 of the current points that I'm at, plus I now look backwards to ti and then j minus 1 all over delta y squared. So I'm changing, in this case for my dx, I look left and right, but at the same y, and for my second derivative with y, I look up and down without changing the x. Okay, so now I have numbers I can substitute in to that top equation. So we can say ti plus 1 comma j minus 2tij plus ti minus 1 comma j all over delta x squared, plus, now I put in my delta, my second derivative temperature with respect to y, I get ti comma j plus 1 minus 2 ti comma j, I comma j, plus ti j minus 1 all over delta y squared equals 0. Okay, so this is going to look like exactly like we had before for my boundary value problems, but notice that I have to keep track of two indices, the x and the y index, and I need to input them appropriately. Okay, so I can now take those, clean that up just a little bit, and we can have this equation. So if we have an evenly sized grid, so let's say we say dx is equal to delta y. If I set this up such that they're even, we can go in and multiply through by dx squared and then sum the terms, and we get the formula ti plus 1 comma j plus ti minus 1 comma j plus ti comma j plus 1 plus ti j minus 1 minus 4 ti comma j equals 0. Okay, so this is now my form for solving all of these points at all these nodes, right? I can write out a version of this for every single point on this graph. Okay, and so we can then solve this out using linear algebra or the Gauss-Seidel method. So we're going to tackle these each in turn. So let's look at the linear algebraic solution first. So first we need our heat equation. I've written this out here. Let's tackle this point 1 comma 1 first. Okay, so we're going to look to the left. So we're going to first look, to the right. So we're going to look over here to this node. So that's T2 comma 1. Plus, now we're going to look to the left. Oh, that's a boundary condition, right? Let's say it's 75 degrees C. So we put in a 75. because that's what's to the left of us. Now we go up. So now I'm going to look up. What's my value here? Well, I don't know that value here. It's just t at 1, 2. Then I look down. That would be this node here, which would be 1, 0, but that's just 0. So I can put that in here for 0. Minus 4 times where I currently am, so t 1, 1, and that equals 0. So I can clean all of this up and put them in a nice linear algebraic formula. So I could say -4 t11 plus t12 plus t21 equals -75. Okay, so I can go through now and I can do that for each of these points within this grid where I look left, I look right, I look up, I look down, and then I rearrange to get my variables on one side and any constants on the other side. So I can repeat this for all of these different points. If I do that, I end up getting a whole set of linear equations. So this, so we have 9 linear equations, one based on the equations written out at each of these different points. And you see that we form a nice matrix. We actually have this nice banded matrix. So once we have this matrix math, well, we can solve that. And at this point in the semester, we know lots of different ways to do that. We could do back division. We can do any of those different techniques that we've talked about. Now let's go in and do this again with the Gauss-Seidel method. Here, remember that when we remember back to solving our nonlinear methods, we would take this equation, isolate one of the variables on one side, so say right here, and we would have this nice functional form. We would have this nice functional form. And we had talked about the fact that if this can be quite slow and tedious as we're going through there, so we can go in and try to make that faster by using over-relaxation. Remember, we would the idea was we would calculate a new Tij using this the equation that we had just set up, and then we would multiply it by this lambda, and we would mix essentially the new value and my old value, right? Where our lambda is our weighting factor between 1 and 2 for over-relaxation, and 0 and 1 for under-relaxation. Let's say we were starting to get oscillations, we might want to set this lambda to be less than 1 so that it sort of dampens out our oscillations, and we get a convergent solution. With this Gauss-Seidel method, we can, of course, calculate what our error is at each of these points using my old values and calculating an approximate error. We would then repeat the process again and again until we find a converged solution. Let's go ahead and give this a spin. Let's take that same problem where we have a boundary value problem where we have 100C up here, 0C over here, 75C here, and 50C here. And we're going to solve this at these 9 points. Remember, for Gauss-Seidel, we have to have an initial value. We have to have an initial assumption for what these values are. In this case, let's assume that all those interior points are 0. This is not a very good guess, right? Because if you just sort of look at this functional form, we can see that Tij, so each of these points is essentially the average of the points surrounding it. Because the edges are all, because most of these edges are all much higher than 0, we don't anticipate that these internal points are going to be 0. However, for the point of this exercise, let's just pretend that we're going to start with 0, and we'll see how we go. Okay, so the first step is to apply this point to maybe this 1, 1 point. So we can say that T11 is going to be, first I'm going to look to my right. So it's my temperature here, which is 0, plus my temperature to the left, which is 75, plus my temperature up, which is 0, plus my temperature below me, which is 0, all over 4. Okay, when I do this out, that's 18.75. So this is my next guess for my temperature. Now I'm ready to do my over relaxation. So I can say that my actual next guess is going to be lambda, which is 1.5, times my new guess of 18.75, plus 1 minus 1.5, so 1 minus lambda, times my old guess, which was 0, and this will give me my actual next guess, which is 28.125. Okay, so remember, this over relaxation should hopefully get us to the right answer faster, right? So instead of just having 18 as my guess, I'm actually getting 28 as my first guess. Now I can go ahead and do this for each of my points. So I can move over to point 2. I can either move over to point 2 next, or I can move up to 1, 2 or 2, 1. The choice is up to you, but remember that sometimes that choice matters. Sometimes you'll get a faster solution going one direction over the other. It sort of depends on the problem. But let's say we go up to point 1.2. I would look left to 75 degrees. I would look down to that 28 degrees, look right to 0, look up to 0, and I would get a value of 38 degrees C. I can then go up to 1.3, that would give me 80 degrees C, and then I can continue on looking at each of these points in turn. Okay, so after I go through my full first iteration, I end up having an error of 100%, right? I've gone from having zeros everywhere to a bunch of new numbers, so that's a 100% error. Now I can go ahead and I can do this for a second time. So I start again at 1, 1. I do my right look, my left look, up, down, get a new value, and use over relaxation to do this for each point. So after my second time going through everything, I have an error of 13.5% for T1, and then going to repeat this until my error everywhere is less than 1%. After a few iterations, I end up with these values. What we'll find is this gives a maximum error of 0.71% across these values. So we can say that this is our final temperature distribution within our box or oven or however heating plate, whatever this system of equations is representing. Okay, so just sort of going back and sort of remembering to when we were solving Gauss-Seidel equations, remember that our initial guess does matter. So we had said everything was zeros. Maybe a smarter thing would have been to say interpolate between these guesses, just a nice linear interpolation, and we probably would have gotten to the answer much faster. Okay, so let's go ahead and address this again using our sort of finite points, our nodes, but let's address this using a derivative or our Neumann boundary condition problem. This time, we still have our nodes on the left being 75 degrees, our nodes on the right being 50, and our nodes at the top being 100. But this time, we're going to say that our nodes on the bottom are going to be have this condition of dt dy at y equals 0 equals 0. Okay, these are going to be our points. So what we need to do is add in a set of imaginary nodes. These imaginary nodes are going to control that temperature, control that at give us our boundary condition. So we're going to implement an imaginary node where we need it. Okay, so how we're going to do this is remembering what my numeric form of my derivative is. So we can say that t partial x is t1 j minus t negative 1 comma j, right? Because this would be for t0 comma j. So any point along at 0x at any point of j, I can say that, so at 1 and minus 1, so that's going to straddle that 0. These j terms here are covering for any point along x, along y is 2 delta x. And we said, and we can rearrange this, of course, to say that my point at that imaginary node is going to be t1 comma j minus 2 delta x partial t partial x, or put this another way, this, because delta t delta x is 0, this is t1 comma j. So I can plug this in. If I'm looking at that 0jth node, I can plug this equation in, and we can say that we have t1 comma j plus ti minus 1 comma j plus t0 j plus 1 plus t0 j minus 1 minus 4 t0 comma j equals 0. I can plug in this equation here, so we would get t1 comma j plus t 1 comma j minus 2 delta x partial t partial x plus t0 j plus 1 plus t0 j minus 1 minus 4 t0 comma j equals 0. And then in this case, if we say that that derivative is 0, that just goes away and we end up with 2 t1 comma j's plus t0 j plus 1 plus t0 j minus 1 minus 4 t0 j equals 0. Okay, so in essence, we just have a slightly different functional form for those edges where we have a derivative boundary condition, but the idea is going to be the same. So we can go ahead and repeat the steps that we had before using that initial value, those boundary value problems in Gauss-Seidel, and we'll find a slightly different solution shown here on this map, and I've added in arrows to show what those gradients are. So that's just to show how things are going to go. We could do the exact same thing using those imaginary nodes in that modified equation for the linear algebraic solution. For our interior points, we still have this same equation that we had before, but now for our insulating points, we have this equation. Here's that 2ti. Here is looking left and right. This was looking right up and down at that t0 point using that derivative boundary condition, and we have minus 4ti0 equals 0. So in terms of derivative condition, just like with boundary value problems, for partial differential equations, we end up having to input additional elements into our matrix for solving these problems. Okay, so sort of backtracking and summing up boundary value partial differential equations, it's going to look just like our boundary value problems that we talked about so far, but in this case, we have that extra piece of needing to look in multiple dimensions and not just left or right. So we're still going to use either, we're still going to take at each of our nodes and come up with a substitute in finite differences for each of the node points. We're going to look left and right, but now we need to look, say, up and down as well. We're still going to then write out that equation for each individual point, apply the appropriate boundary conditions, which may require writing out an additional equation that needs to be considered, and then solving that set of equations using either linear algebra if we have a linear solution, or something like Gauss-Seidel if we have if we need to take nonlinearities into account. I'm not going to go in and do examples for nonlinear cases or more complicated cases because it's just extensions on what we spent a lot of time on in the boundary value problems. And I want to go and discuss time dependency and how we can bring that time dependency in. Just remember, as we're manipulating these equations, we can put in any of those number sets, or we can convert any of the equations given into a set of linear equations or a set of equations using finite difference definitions. Okay, so now I want to talk about bringing in time dependency. So previously we had, we just had two boundary value problems essentially. Now we're going to talk about a case where we have a time dependency and a boundary condition. So in essence, this is an initial condition problem, and then this is a boundary condition problem wrapped together. We can say, we can have additional terms out here, whatever. So we can use the same ideas as we did before, but this time, instead of doubling our boundary value problems, we're going to integrate both initial condition problems and boundary value problems. So we're going to once again go ahead and we're going to break our problem up into different nodes. We're going to convert our PDE into numerical form, and then we're going to solve in the 2 dimensions. So let's take a simple heat conduction problem. Here we have K, so some constant times my second partial derivative of temperature with respect to X, and second derivative of temperature with respect to time. Here, I've drawn out a whole bunch of different nodes in the x direction, and then this time going up, we have time. So this should look quite similar to the boundary value problems, the double boundary value problems that we had talked about previously. So now we're going to use our definitions to convert this into a series of simultaneous equations. So let's first tackle this right-hand piece. So partial squared time, temperature, partial x squared. This is just like we had before. So this is now T I plus 1 minus 2 T I plus Ti minus 1 over delta x squared. I'm going to use one additional notation. Here, I'm going to put an L up top. This is going to represent our time as I move upwards. Notice that I'm putting it up in the top corner to represent that this is a time piece and not a y piece, right? So I'm moving forward in time with these variables, so time, and I'm moving in space with these variables down here. Okay, so we've taken care of this piece. Now we need to take care of this time piece. So let's look. So partial t partial time is, now we can just use our forward finite difference, because we don't need to go, we want to use a forward finite difference because we need the next point. So we need to have that I plus 1, and it needs to refer to this point back here. So we can say that my next point, so L plus 1 at any point of I, minus my temperature at my current time step over my change in time step is equal to that derivative. So with this, I can go ahead and wrap these all together. Okay. Sorry. So we can go ahead and we can wrap this all together. So I can write this out. I can get k t I plus 1 at time L minus 2 TIL plus T I minus 1L over delta x squared is equal to TIL plus 1 minus TIL over delta t. Now I can pull those pieces together. So we can, using those definitions, we can say k Ti plus 1L minus 2 TLI plus TLI minus 1 over delta x squared equals TL plus 1 over I minus TIL over delta t. And now I'm going to rearrange these pieces to isolate my next step. So I want to isolate this next step. Okay, so I need to move this delta t over and this t1 over. So when I do this, we get ti at time L plus 1 is equal to Ti at L plus delta t times k over delta x squared times ti plus 1 at L minus 2 ti at L plus ti minus 1 at L. Okay, and I can simplify this a little bit further by just sort of lumping all of these terms together, and we can call this lambda to be k delta t divided by delta x squared, just so I don't have to keep writing all these constants out. So what you'll notice if I look at this equation is I have sort of two pieces. If I look at this piece, this looks like an initial value problem, right? So if I think of Euler's method, I have my next time is my old time plus my change in time times some derivative. Then within this piece, we have, now this looks like a boundary value problem where I have multiple pieces sort of looking back and forth on each other. So we've got this sort of combination of initial value problem, boundary value problem, which is unsurprising because that's really what we do have. Today, there's multiple ways to approach this, but today I'm going to talk about the explicit method. So what we're going to do is I'm going to zoom in. I've zoomed in here on some different nodes. So here's my different x's going across this way. Here's my times going up here. We're going to talk about the explicit method. So we're going to solve using these different points. So these 2 points along the time thing where these x's are going to be my grid points where I'm going to solve for my time difference. And in my explicit method, I'm only going to use my previous points in space to move, and I'm going to do that only using my previous points in space. So here I've got these 3 points. I'm going to look backwards, see what the temperatures were there, and then move forward in time. There's other ways to do this, and we'll get to that next time. So let's set up our time. We can say that we're going to have a set of grid points to solve out a problem. Here we're going to look over 10 centimeters. We've got, say, 0 here, 10 out here, and we're going to go in increments of 2. So here's 2, 4, 6, 8. So this is me setting up my x nodes. Then we're going to go forward in time in increments of 1 second. So I can say maybe this is 0.1 seconds. So we're going to go forward. So there's we're going to look at each of these pieces, and we can then go forward in time. Okay, so now we need a set of equations. I've pulled that temperature equation forward for what we've solved for so far. So we can then start writing out the equations at each of our nodes. So let's take a look. So let's call this, right? So this is going to be T11. So T at x1 time 1 is equal to, we can put it down here. So x equals 2 and time equals 0.1. We can now go in and solve our, put in these equations. So we can look at each of these nodes. So at this first point in time, remember our initial condition says that it's 0. So that's easy because that's a 0 plus lambda. Well, lambda is given up here. So we can just plug that in. So we have 0.020875. And now we have our boundary value piece. that we need to solve for. So we need to look right. So we need to look at point 4, but we need to look at point 4 where it previously was. So previously, we said that initially it was all 0. So that's easy. So that goes in as 0. Minus 2 times my previous value at that, also 0, right? Because that was the initial value. And now I need to look backwards to the edge. Well, this case, this edge value, right, is 100 coming from that boundary value condition. So I have a plus 100. Okay, so this point in time, we have zeros, these 100, 0, 0, 0, 0, 50. I have to look backwards to these 3 points. I can solve out all the math, and when I do, I get 2.0875. Okay, so I can do this again for each of my different time points using this equation. Remember, in that first step, initial conditions, we had these points 0, 2, 4, 6, 8, 10. And this was 100, 0, 0, 0, 0, 50. So when I go to, when I look at point 2, right? So we did that on the previous slide. We looked backwards. When I go to solve out T21, I need to look back to this point, which is 0. So it goes 0 in here. I look back to itself, which was 0. And I look back to the point on the right, which was 0, to give me 0. When I look at point 3 at my first time step, I look back to point 4, 0. I look back to itself, 0. I look back to the previous point to the right, which was 0. Then when I get to point 4 and that next step, I look back to this point, which was 0. I look back to itself, which was 0. And then I look back into the right. In this case, it's 50. Right? I can solve this all out, and I get a new temperature of 1. So notice how these interior points are not heating up quickly. They're sort of stuck at 0. Right? So I can do this again for time t equals 0.2. And we can see that those interior points start heating up. Okay, and then I can repeat this again and again and again, and I can look at this over time. I can then graph what this looks like by plotting those different, several different time points on that same graph, on that same x graph, and we see that we have these points, and they start moving sort of up in time. Okay, so what I want you to also notice is I'm only plotting these at times 3, 6, 9, 12. If you remember back, we were taking time steps that were 0.1 second. This is because these combinations of initial condition boundary conditions can be very fussy. Right? So we have to take very small time steps because we're having to look backwards and move forwards, look backwards at multiple points and move forward at the same time. So these problems are going to be much more dependent on our step size. And so that's what I want to talk about a little bit. So there's 2 types of ways that we can measure how good our approximations are. One being convergence. And that means how well do our results are approximated as t and x goes to 0. So how rapidly, as I take smaller and smaller time steps, do my error fall off. So let's say maybe this is 1 over x, so as or maybe this is my h, this is my delta x. If I have a really big delta x, my answer should change relatively rapidly, but then as I get smaller and smaller x's, I should eventually converge to a solution. This is called convergence. So how quickly do we get to this flat point where if I make a small step, it doesn't change my behavior? We also have stability, which means how do my errors propagate? So if I make a small error, does my error get bigger and I sort of just go running off to anywhere, or are my do I sort of catch back up and I get more stable? So I'm moving out of this oscillatory regime into a more convergent stable regime. The key is looking at the relative sizes of this time step and my x step. So in relationship to my different variables. So I need to make sure that my time step is quite small compared to my x step, modified, of course, by how rapidly heat is coming in. Remember, this K was saying how quickly heat moves in and out. So the faster that this is, the bigger that this K is, the smaller my time step needs to be to have a convergent solution. So I need to have, if this number, so if I'm dividing by a big number, my time needs to be quite small. If I'm having rapid changes, my time step needs to be very small. Okay, so as long as this is less than 1/2, I should be both convergent and stable. However, we may still have weird oscillations in the result. It's better to set that lambda, so it's better to set delta t to be less than 1/4, where that is equal to 1/2 over delta x squared over k. So really, we want this to be much smaller. We want to have much smaller time steps. And this will ensure that we won't oscillate. And we really want to go even smaller to say lambda is 1/6 to try to minimize truncation error. So in summary, talking about convergence and stability, we want to make sure that our time step, so every step that we're moving forward, is very small in relationship to my x, my boundary value problems. Okay, so let's sort of review. So we talked about finite differences, we covered what a Robbins boundary condition is, and then we talked about explicit time-dependent problems. We can make these, even though they're called time-dependent problems, what they're really talking about is a first derivative, an initial value first derivative problem. So maybe dz dy is plus d squared z dx is equal to some function of x, y, and z, right? This would still be considered sort of a time-dependent problem because, or an initial value problem because we have this, initial value piece, we have this boundary value piece. So even though we only covered the case where we sort of considered this y to be, a time, it could be another space variable. with an initial condition. We also covered the cases where we had two boundary values, so maybe dz squared d squared x plus d squared z dy squared equals 0, where we had two boundary value problems stuck together. We used finite difference methods, where we took these problems, we converted any derivative into a finite value piece, and then rearranged those pieces to isolate one piece of information at the node that we're at, and then we could do either linear algebra or a Gauss-Seidel type approach. Okay, I hope this is starting to make sense. I'll see you in class, and then we'll pick up these types of problems next time.